My name is Jenny Plunkett, and I'm a developer relations engineer at Edge Impulse. In today's workshop, we'll be going through how to run a novel machine learning object detection model on a microcontroller like the HiMax WEI Plus. For this demonstration, you'll need one of the officially supported development boards with a camera attachment that we have listed on our Edge Impulse documentation site. Today, we'll be using the HiMax WEI Plus, but you can also use your mobile phone, your computer, a Linux board with a camera attachment, or any of the microcontrollers that we have listed on our website. Edge Impulse is the world's leading embedded machine learning platform. The Edge Impulse Studio covers the full end-to-end machine learning pipeline to accomplish a variety of ML tasks from regression to vibration, sound classification to object detection and predictive maintenance. You can import data from any sensor and any device and deploy your model to almost any device as well. You maintain control of your data and firmware throughout the entire process, and your code that you deploy to your device is all open source and available for free from the Edge Impulse Studio. The Edge Impulse Studio covers the entire embedded machine learning pipeline from collecting and labeling your dataset, designing and training your machine learning model, testing your model, and finally deploying to your device. The Studio guides you step by step through the process of creating a precompiled firmware or library that will run your Impulse or your machine learning model directly on a number of platforms that we have officially supported in the Studio. But you can also deploy a C++ library that is open source with no third-party dependencies that can run on almost any platform. The C++ library output contains all of your pre-processing code for your digital signal processing, trained neural network, and any anomaly detection code that you may have so you can perform inferencing locally on your edge device or on your computer without an internet connection. For an in-depth and detailed technical overview of FOMO, or Faster Objects, More Objects, a novel object detection algorithm for constrained devices like our microcontrollers, please head over to our documentation at docs.edgeimpulse.com/docs, where you can find this tutorial. I will briefly go over what FOMO is compared to classical object detection applications, and then we'll go into a deep dive of the studio. In a traditional object detection classification algorithm, you create feature maps from your image and then use fully connected layers to match those features to the images used for training, and then a probability distribution that each class or each object that you want to identify as in the image is the output. And this requires a lot of resources and a lot of compute time. So, in traditional object detection applications, a higher level compute processor like a Linux device or a desktop computer is needed in order to run these object detection applications. Image classification, however, is something that is very similar to object detection, but removes these last few layers of finding the location and the size of the object that is in the image, and is instead just identifying whether the object that you want to find is present in the image, wherever it may be. So, image classification is something that can really be run very quickly and very easily on microcontrollers. So, FOMO solves an interesting problem here where we want to take object detection and image classification and combine the two concepts in order to run them on low compute devices. So FOMO essentially takes a traditional object detection algorithm and removes these fully connected layers and replaces them with a single per region map. This single per region processing map is much simpler and it works very similar to image classification, but you can still find the location of the object and the image, but not necessarily its size. So in comes FOMO, or Faster Objects, More Objects. FOMO is object detection for microcontrollers or MCUs, and it's based on MobileNet architecture. But it's interesting because MobileNet v2 architecture uses almost 11 megabytes of flash, while FOMO only uses 77 kilobytes of flash, 244 kilobytes of RAM, which is perfect for running object detection on very constrained devices like microcontrollers. We've run it on various targets and see very high frames per second, almost 60 frames per second on a Raspberry Pi, or 30 frames per second on a Cortex M7, like the Arduino Nikola Vision. It's really good at detecting small and more numerous objects like nuts and bolts, and it's capable of segmentation and counting the number of objects that are present in the image based on the classes that you've trained for your model. This is a very simple overview of how FOMO works with segmenting the image into various squares and determining the centroids or probability that the object that we want to detect is within that square. So we train on these centroids, and using these centroids makes it really easy to count objects that are super close. And every activation in the heat map is an object over a certain threshold or the probability. You don't need the size of the objects, but rather the number of objects and their position in the frame. For the FOMO model trained here, the size of this heat map is 8 times smaller than the input. And if the input image is 160 by 160 pixels, you'll yield a 20 by 20 heat map. And this is configurable within the Edge Impulse Studio. When you set this ratio to 1 to 1, you can actually achieve a pixel level segmentation and the ability to count a lot of small objects within your image. To follow along with the demo that you'll see here today, please go to edgeimpulse.com to sign up for a free studio account. If you're going to be using a Hymax board or another officially supported board with a camera attachment to follow along with the demo with me today, please go ahead and go to the corresponding board page in our documentation at docs.edgeimpulse.com to install the dependencies that are necessary in order to get started with the Edge Impulse CLI for data collection and for updating the firmware on your device. This is the Edge Impulse Studio dashboard. For every dashboard in the Edge Impulse Studio, it is equivalent to one machine learning project or one embedded machine learning project. Today, we'll be doing an object detection FOMO project created by one of our Edge Impulse experts, Peter Ng. And this project is essentially going to be determining what number of washers, bolts, and nuts are in the frame of our Hymax board camera. So this is our dashboard where we can navigate how we can create our first impulse, how do we acquire data, how do we upload our images to our project, how do we design and train our impulse, and how do we deploy it to our Hymax board. So I've already connected my Hymax board to my project, and you'll be able to see it on the Devices tab. But I did this by running the Edge Impulse CLI, and all of the information can be found in the Hymax or the officially supported board that you're using's doc page. So I've updated the firmware on the Hymax device, and I have opened my terminal application and run the Edge Impulse Daemon CLI application. So I already have my Hymax board connected to my project, and you can see here via the green light. You can also collect images via any other source, like your phone or your computer's webcam. Today, we'll be collecting images directly from the Hymax camera via the Edge Impulse CLI into my project. So I'm going to move on to the Data Acquisition tab. And this tab is where we can see all of the existing samples that we have uploaded. Here we can see Peter has uploaded a bunch of samples where he's labeled the location of a washer in an image. Today I've also uploaded a few images directly from my Hymax camera into the project, as you can see here. These images are unlabeled and we'll label them via the labeling queue for my FOMO application. On the right side, under Record New Data, you can also see all of the devices that you currently have connected to your project. I have my Hymax board connected, and you can see a live camera feed when I move my device above my computer. And I can go ahead and take another picture of these two washers that are on my desk. It takes a snapshot, and it reads the data over serial terminal and uploads that to my project. Now I have a brand new sample in my dataset. So we'll do this for a bunch of items for both our training dataset and our test dataset. Once we are done adding all of our data, it's going to be mostly unlabeled. So we're going to move down to the labeling queue and draw our bounding boxes over the objects in our image. That's a bolt, and this is a washer. You can also use the Edge Impulse tools to automatically track objects between the frames to assist you with your labeling process. Or you can also classify your objects with YOLO v5 to make the process of labeling your images even easier. Continue this process until all of our images are labeled. Great. Now we've labeled all of our data, and we're going to go through and start training our model. This is the impulse design page. This is basically a graphical representation of the machine learning pipeline that you'll have for your model, all the way from collecting and labeling your data set for your image data on the left in the red, extracting the most important features of your image via digital signal processing in the white box, creating your model based on the extracted features from your digital signal processing block, and creating your FOMO object detection model in the purple there. And then finally, you'll have your output features, which is the three classes we trained for your model, the bolt, nut, and washer, and the location of those objects within your image. And we'll deploy that to the HIMAX board. For image classification projects and object detection projects, we'll use the image digital signal processing block. We'll use the image digital signal processing block, and this is basically just a GUI that is wrapping over a Python script that we created for your free use within the Edge Impulse Studio. All of these scripts for these digital signal processing algorithms are available in our Edge Impulse GitHub repo, which you can find on our website. So we're going to just save these parameters, and because FOMO is designed for low processing power microcontrollers, we're going to make sure that our images are in the grayscale color depth. So it doesn't require as much processing power to extract the most important features of our image. We're then going to generate our features, and this is what our feature explorer looks like for our nuts, bolts, and washers class. We have a pretty good segmentation over here that we can see on the right. We can also see our on-device performance, in which case this image processing algorithm only takes 7 milliseconds of processing time on a Cortex M4F device and only 4 kilobytes of RAM. Moving on to our object detection block, this is where we'll train our machine learning model. Here we've just selected our model for FOMO. You can choose a different model here, but you'll want to choose FOMO for constrained devices like microcontrollers. And today we've selected the MobileNet V2 0.1 model, but we also have Alpha 0.35 available for you as well. You can also see the classical MobileNet V2 model here as well for larger object detection applications for Linux devices. So we just set our number of training cycles, our learning rate, and our validation set size. We can also do data augmentation, which randomly transforms the data during training, allowing us to run more training cycles without overfitting, subsequently improving accuracy. So I've just selected the Start Training button. You can also see Expert Mode on the right here. If we go up to the top and click Switch into Keras Expert Mode, we can see the exact Python code that was used to generate this model here on the right. Switching back to the visual mode. On the right, we can see our confusion matrix for the accuracy for our object detection model for FOMO based on the classes that we have trained our model on. And in this confusion matrix, we can also see the percentage of accuracy versus how often the model correctly identified that the object in the image was a bolt, nut, or washer. And this percentage is coming from the validation set or the subset of samples that was taken from the training data set, taken out and re-identified on the model as it was trained in the Edge Impulse Studio. This is different from the testing dataset, which you can see on our live classification tab or our model testing tab. From the live classification tab, we can directly connect to our HIMAX camera, see our camera feed, and start directly classifying without having to deploy any model to our device. We can take an image from our HIMAX board camera and pass this image directly into our model that we've just trained. Then we'll be able to see if our FOMO model correctly identifies the washer in the image. And it did. But it also identified it as a nut as well, meaning that we may need to add more samples to our training data set in order to further increase the accuracy of this model. We can also bolt test our testing data set on the model that we just trained in the studio directly in our web browser by navigating to the Model Testing tab and passing all of our testing data into our trained model. This will output an entire list of all the test data set samples that we have, their expected outcome, and the result that we've got after we pass the test samples into the model that we've trained. We can also move on to the versioning tab. Say I really like how this model is performing and I want to try it out in the field, but I want to make sure I can go back to this model at any point in time after adding more data to my data set in the future. to further increase the accuracy of this model. I can just go to the versioning tab on the bottom right here, and then click Store My Current Project Version. This takes all of my intermediate project data, all of my configuration, all of my intermediate results, and model information, stores it up into essentially a zip file, and I can go back to this version at any point in time in the future by navigating to this page and restoring from a specified version. If you're making this model and you want to share it with the world on social media, you can also make it public, and that will provide you with a public project link that you can share on social media. People can clone this project directly to their own Edge Impulse accounts and further iterate on the model that you created. Now, moving on to the deployment tab, we can see here that we have a bunch of different types of libraries that we can deploy our model to. We can deploy a C++ library that contains all of our digital signal processing code, all of our trained model information, and everything that you need in order to get us started doing object detection on your microcontroller. And this can include any microcontroller that we don't necessarily officially support on the Edge Impulse website, but you'll need to do some more work to integrate your camera driver into the Edge Impulse SDK. But we have more information about that in our documentation. Today, because we're using an officially supported board like the HiMax camera, we're going to select under Build Firmware the HiMax WEI Plus. This is going to create a ready-to-go binary for directly flashing onto our HiMax board, and we can get started doing object detection with our nuts, bolts, and washers model on the edge in as little as one click to flash our model onto our board. All of the firmware for these boards is available in our GitHub repository, where you can directly drag and drop your C++ library for your Edge Impulse SDK in and out into these pre-written SDK examples as well. And all of that is available in our GitHub repo. So I'm going to build this pre-built binary firmware for the HiMax board. I'm going to scroll down and select our Eon compiler and quantization optimizations. I'm going to select int8 quantized build, and this will generate a pre-built binary that I can directly flash to my HiMax board. Then, using the Edge Impulse CLI, I will start the model or the proof of concept application, and I'll get started doing object detection on the edge. Similarly to what we did earlier to collect data off of our HiMax board, we use the Edge Impulse CLI and the Edge Impulse daemon command to connect to our project and collect images off of our device. In order to run the firmware that I flashed to the board, I am now going to type in the command Edge Impulse run impulse. And this will directly launch the proof of concept application that I've flashed to my HiMax board. And we can start seeing the FOMO model to identify the washers, nuts, and bolts on my desk in the HiMax firmware, directly on the edge without an internet connection. And my model has directly identified that there is a screw on my table in the coordinates specified. And now we're running object detection directly on the edge on our HiMax microcontroller using FOMO by Edge Impulse. For any further in-depth technical questions that you have about today's workshop, please go ahead and ask us on our forum at forum.edgeimpulse.com. And please sign up for a free Edge Impulse account at edgeimpulse.com. Thank you.